Welcome to the Axiom, a immersive learning experience designed for learners to examine a concept in many multiple dimensions. It is often the case that as learners we would like to examine a particular concept from many dimensions and perspectives. Maybe some visual analogy that will help me to better understand a difficult concept, some historical timeline, a narrative that is spoken, many different modalities in which I might require information which might be helpful for concepts. And some modality may be like more helpful for certain concepts, and some other modalities may be better for other concepts too. So therefore, having the choice to work with all these different options would like increase the chances that I would settle on a modality to better understand any given concept. Now that is the premise for developing Axiom, and for any given concept and its brief scientific definition. Axiom sets about generating a multimodal resource around that concept and definition. In effect, generating a knowledge universe in which the learner could immerse themselves and make sure that they learn the concept. So this is like an application phase in knowledge development, and so this goes hand in hand with let's say a case study sort of a learning as well. So this is complementary to a case study. It's a applied phase in the learner's journey. So let's try to demo the axiom and go through its features, especially how it can offer explanations at multiple levels for all concepts like beginner, intermediate, and expert, and the other sort of dimensions on which it offers its knowledge. So let's try a concept here. I'm going to go with non-Euclidean geometry for the concept, and for its definition I'm going to say this is a type of geometry that basically violates Euclid's fifth postulate, that is parallel lines never meet, right? So we have two types of these, and let's see how it does on this particular concept. Now it's now constructing the knowledge universe for non-Euclidean geometry, and let's see how this turns out. It's going to take a little while to generate all the resources. So we'll wait a minute or two. So it's still generating and constructing the knowledge universe that we have asked it to provide for the concept non-Euclidean geometry. So I think it may just take less than a minute from now. Anytime now, I think we are going to see all the resources it has generated that the learner could then browse and gather more information on this concept that where they have a genuine confusion. So thanks for staying with me. It's almost hitting the 2-minute mark. Oh, here we are. So it has now completed its process, and it has given us back the learning, a immersive learning experience, a knowledge universe around non-Euclidean geometry. So let's just like briefly browse this and see what it has come up with. So first it gives a core explanation for the concept, and it pitches the core explanation at three different levels. Suppose a curious beginner or an engaged learner or a deep scholar, right? And it provides a very simple synopsis and then provides some facts that might be interesting to readers. Now you could listen to this synopsis that it provides.
Non-Euclidean geometry is a way of measuring shapes and distances that works differently than the flat geometry you learned in school. Imagine drawing triangles on a basketball versus on a flat piece of paper. The rules are different. On curved surfaces, parallel lines can meet, and triangles don't always add up to 180 degrees.
Alright, so that was the sort of a understandable explanation if you're a beginner to non-Euclidean geometry. So if you're a engaged learner, it provides a slightly more elaborate and technical account of that, and this can also be like converted into audio. You just hit the listen button here and it's going to take off.
Non-Euclidean geometry refers to geometric systems that reject Euclid's parallel postulate, which states that through a point not on a line, exactly one parallel line can be drawn.
Alright, I'm going to stop it there, right? So so we do have this option to narrate the this overview, and then we have something for the deep scholar as well. Now you can see the analogy that it generates for this, and it tries to provide a visual analogy that can carry us through in understanding the concept. So it says these are the three kingdoms of geometry, where the same journey takes different paths. So Euclidean is the flatland, hyperbolic is the saddle kingdom, and elliptic is the sphere empire. So this is a very nice visual analogy of the kinds of non-Euclidean geometry, right? Where Euclidean geometry refers to the default geometry that we are most familiar with. So it provides this mapping between the analogy and the concept. Roads and flatlands are parallel lines in Euclidean geometry, and then kingdom paths where these curve away. Those are the parallel lines in hyperbolic geometry. So like that, like you have some of these analogies. What is the expansion rate of circular borders? Circumference as a function of radius. And you see this is really a very nice analogy for all these concepts. And so it also provides a card-like representation for each of these maps, right? So that there's some text to go with them as well. So it provides a complete analogy to try and understand this, and gives us the analogy mapping diagram. Then it enumerates the key principles associated with this concept, and you can see all of that here. And then where are the applications for this concept, the different areas and subjects, they're all listed. And then some timeline for this non-Euclidean geometry, starting with Euclid, and then like Bolyai and Riemann, who came up independently with this idea of non-Euclidean geometry. So you also see a web of all these different links, and you can see how it relates with other subjects. And then what are some myths associated? So non-Euclidean geometry is inconsistent or wrong, while only Euclidean geometry is correct. And what is the truth behind this misconception? Tap to reveal the diagnosis. So that's what this says, and we can just tap, and you see reality is that all three geometries are equally valid logical systems. They simply describe different types of spaces, right? So it provides another little account here. Our everyday experience is overwhelmingly Euclidean, that is flat. So therefore we don't have the intuition necessary to perceive non-Euclidean geometry, and it seems counterintuitive, but it's just as mathematically rigorous. So that's what is really given here. And similarly, you can see a few more misconceptions and their diagnosis, and some additional notes as well, right? So that's really another useful addition to the knowledge universe. And then there's also a code lab, and if there is some calculations associated with the concept, provides the code for the calculation, or if there's a visualization, it provides the code for the visualization. So simulations, visualization, calculations, most of these are usually associated with any scientific or mathematical quantity. So in the code lab, we'll find the Python code for such things to do. And you can see this, it provides some code for Poincare disk model of hyperbolic geometry, which is really a would serve to reinforce the learning by a long way. Alright, so it provides a lot of these codes that will be useful for really understanding the concept better and the associated concepts. It also gives the expected output for all the codes. Now finally, there's a quiz you can take, or I can take, and then you can keep answering the quiz. There are 5 questions, and you can see what score we make. So let's go through this quickly. How many lines fell to a given line can pass? Infinitely many. And so therefore score is 1 by 1. So what is the sum of triangles in a sphere? So this is greater than 180 degrees. So again, it is greater than 180. So what property determines whether the space is Euclidean, hyperbolic, or elliptic? It is the Gaussian curvature of the space. So that's great. So k less than 0 for hyperbolic and k greater than 0 for elliptic. Those are the negative and positive curvatures, whereas for Euclidean we have it as 0. So the Poincare disk model represents hyperbolic geometry with an Euclidean disk. So what represents straight lines in this model? Let's say these are the logarithmic mass. No, those are actually arcs of circles perpendicular to the boundary. So that's fine. So we don't know. So our score is 3 out of 4 so far. That was the tough one at a higher Bloom's level. So how did Einstein's general relativity utilize non-Euclidean geometry? So basically, Einstein describes space-time as a curved 4D manifold where mass creates the curvature. And so that's the right one. So that's my final score. Now I can narrate the summary for this concept in this narrate summary.
Non-Euclidean geometry emerged from a millennia-long quest to understand Euclid's fifth postulate, ultimately revealing that multiple consistent geometric systems exist beyond our flat everyday experience. Non-Euclidean geometry emerged from a millennia-long quest to understand Euclid's fifth postulate, ultimately revealing that multiple consistent geometric systems exist beyond our flat everyday experience. By allowing parallel lines to behave